Thank you all for being here. Today we have the pleasure to have Vahid from the Max Planck Institute presenting his work on machine learning applied to reduced order modeling. And thanks a lot, Vahid, for being here and for having the time to do this while working at the Max Planck Institute. So the floor is all yours. Thanks.
Hey, thank you, Matthew. Introduction. So yeah, okay, let me just briefly introduce myself. Okay, the only thing that I need to just add is that, I mean, Max Planck Institute is a very big society in Germany, and we are specifically, I'm working in the dynamics of complex technical systems branch in Magdeburg, close to Berlin. So the work that I'm gonna present today is called Kernel Methods vs Neural Networks, Nonlinear Methods for Reduced Order Modeling of Thermospheric Density Field. So this is the second work in this context that I'm working on. The first work was to just briefly introduce, introduce the whole pipeline of the project, and this is specifically about one part of the project. So I can just go through the problem statement. So the idea is that in the lowest orbit, in the altitude of around 100 kilometers to around 2,000 kilometers, this is the region which is so interested for the commercial satellites and also some Earth observation satellites. And because of the new advancements in the satellites, I mean, we are witnessing a huge amount of launches in this region. And so in the following years, we have to deal with the huge traffic in low Earth orbit. And most of the, not most of, but this region is just composed by a number of operational satellites, which are working right now, and a lot of operational components, which can be the disposals of the previous launchers, or some satellites that actually are out of order currently. So the idea is that previously they had some specific methods to just determine the orbit of the satellite. But nowadays, since there are many more objects, we have to just tune this accuracy of point locating of the satellite. In this region, it's low orbit region, we have different kind of perturbations that among all of them, thermospheric density is the highest, has the highest contribution. So, I mean, when I'm talking about the density, okay, I mean, just imagine that on Earth we have 1 atmosphere density, and in that region it's about 10 to the minus 12, 13. It's too low, but when you just leave the satellite for a couple of orbits, then it just shows itself. So what we are doing in this project is that we are planning to tune our knowledge on the density in this region. So currently we have some models, some physics-based models and some empirical models. But these are just suffering from either efficiency or accuracy. And we decided to just come up with another idea of having a gray box model for the density in this region to just compensate this between these two. So in the first project, we just came up with this idea of finding a differential equation for the density in this region, and then be able to predict the density and eventually determine the position of the satellite much more accurately. In this pipeline that I just described, we have two major sections. The first section is just the compression. So we have a bunch of data, which is the density in the different altitude and different latitude and longitude. And we want to just compress this data to be able to just play with it, because now we have, in the paper, I will describe the the data set, the data size. But for now, it's just sufficient to say that we cannot play with the original data. So the first step is just compress the data and describe it in a lower dimensional state. And the second step is the prediction, to just find the governing differential equations on the data, on the compressed data. The whole pipeline was described in the previous paper, and in this paper we just focused on the first section and the compression. One of the most popular methods in this domain of dimensional reduction is the PCA. And this method is based on the fact that we can just sort all the snapshots of the data. So for example, we have the data, the density data at time t0, and then we just put the data on the for the t0 plus tau, something like that. And then we just collect all this data in a matrix, which is called here is capital X. And then we perform a singular value decomposition, which means that we are just finding a diagonal matrix sigma in the middle and two matrices in the left and right, which the left one contains the eigenvectors of the system. So we can just and then this U matrix has dimension of d times d, and let me just introduce that the data has the size of d. This matrix has the size of d times ns, and ns is the number of the snapshots, and d is the dimension of the system. So and this left vector has a dimension of d times d. And when we are talking about this order reduction, the whole idea of this singular value decomposition is that these eigenvectors, these columns of this vector u, are sorted based on the variance that they contribute in the matrix X. So when we are performing this reduced order modeling, we can just take the first R columns of U matrix. And by this first R columns, we are just taking the highest contributions on this data sets of X, you know. So just imagine that this D for the density case is around 1900, and we can just express it with the first 10 columns. So we are reducing the system from 1900 to 10. And that's why I'm saying that the compression part is very important. And then we can just use this equation to just find the reduced order states. This is a method which is completely linear. The next method that we are talking about, which is the most importance of the paper, is the Kernel Pca. So it's the same PCA, but it's just based on the kernel methods coming from machine learning. And what's the idea? The idea is that imagine that this X that we just came up with here is not capable to be decomposed completely. You know? So the point is that we have some I think you can hear me. Just imagine that we have a nonlinearity in the system, and we cannot easily just decompose the system and express it on some linear manifold, you know. And since it's not doable for some specific cases, we can just take advantage of this kernel-based PCA. And in this method, we are first trying to actually lift the system to a higher dimensional system. So I just put a notation here. So the idea is that which this idea is also counterintuitive, because we are trying to just compress the system, but at first we are just using some nonlinear mapping to just bring this system to a higher dimensional system. But the difference is that now we are just getting rid of any nonlinearity in the system. And then we perform a same analysis that I discussed here, so the singular value decomposition on the new matrix. which is just mapped by this nonlinearity. And here, and the whole this method of KPCA is based on a kernel trick, which is very famous in machine learning domain, and it's based on the fact that we don't need to map all the points of our system based on this mapping function, but we can just compute this form of pairwise similarity comparison based on a specific mapping that we can define. And in this domain, we have a number of kernels, I mean the mapping functions that I just put it here. So actually we are mostly using a function of scikit-learn. So here we have different kernels that you can see here. For example, the linear kernel, when you just use it, the result would be the same as PCA. So it doesn't matter if you're using a normal PCA or a KPCA with a linear kernel, you know.
Okay. And also, do you know why they added it here, just to verify that the implementation was correct?
Yeah, exactly.
I mean, yeah, okay.
Exactly. Just to be sure that it's compatible with their
right.
previous developments, you know.
I see.
And they have also an option of pre-computed, which enables us to just come up with our own kernel, you know. So we can just randomly define a function and then just put it here. But there is a trick here that I may discuss it later. But because if we use this pre-computed one to just come up with our own function, we cannot use a number of functions inside this library. And among the methods, one of them, I mean, the most famous one is the radial basis functions or Gaussian. So the only difference between these two is that this is the form. Maybe I can just maximize. So this is the form of this RBF or Gaussian, and the only difference is that when we are talking about the RBF, we put this beta here as a kernel parameter. But if you want to express it as a Gaussian, you just put instead of this beta, you divide this pairwise squared by 2 sigma squared, which sigma is the standard deviation of the kernel. So instead of mapping all the data points to this new kernel space, which is called kernel Hilbert space, we just compute this k components based on different inputs, and then we just store them in a matrix capital K, which is called gram matrix. And now this gram matrix has a size of ns times n. And then we just use the same procedure. So we just calculate the singular value decomposition perform on this K matrix. And then, like before, we use the first R columns of this V to find our reduced order states. And I need to just mention a few things here. Firstly, of course, during these methods, I mean, it's the same for the PCA and KPCA that we need to just centralizing the kernel matrix, the kernel matrix, the grammar matrix, or in a linear case, we need to just work with the mean subtracted data, you know. So we just in the matrix version, we just call it centralizing the kernel. And as I discussed here, in some papers, they said that this KPCA, I mean, just follow the same rules and different lemmas that they came up with PCA, which also holds in this KPCA. And again, here it's written that again the first arc principal components that can be computed via this method is again just carry the highest variance among all the directions. Did you want to ask anything?
Yeah, I wanted to ask, but I don't know if it's too complicated because it's not clear to me either what I'm asking. But when you talk about variance in the linear and nonlinear method, in the linear one, you're talking about explain variance in the in the physical space, so in the space in which your observations are defined. In the kernel method, the same thing applies, or you have to...
The thing is that you cannot compare these two. So
Right. Because one is the variance in the
the
kernel
definition
space.
is the same, but I mean the quantity that you are acquiring is the same, but you cannot compare them because they are coming from different spaces, you know.
Right. But it's the same. It's the variance, like the Gaussian variance.
The meaning of this variance is the same as the variance that I discussed.
Yes, I see.
Sure. Now we have a big issue here in this method, which is that here in the normal PCA, when we just compute these z vectors, we can easily just matrix multiply this thing by left matrix multiply this thing by UR to just come back to the original space X. But here in the kernel space, in the kernel method, here we don't have X but Kx. So if we just left multiply by VR, we don't get the original space. We just get something random which is not known. That's why we have a huge literature on the backward mapping problem in KPCA. So the problem is that you cannot easily go back to the same space that you had before because of this nonlinear mapping that you had in the KPCA. So you need to formulate this problem in this manner. So the idea is that you say, okay, I have this psi in the kernel Hilbert space in the reduced order states, and you also define this P as a mapping from the original space to the nonlinear space. And now you are finding this X such that you are minimizing this subtraction. And if you have any exact approximation, it means that you are just taking the same point that you mapped before. You can easily just minimize this with the cost function of 0, a cost value of 0, but it's not the case in many cases. So we have to just solve this minimization problem, you know. And the good point here is that we can just take advantage of a method in machine learning called kernel ridge regression. So it's the same idea. So it's a kernelized ridge regression which is very famous in the machine learning domain. So the idea is that we can just change this minimization problem to this one. And the only thing that I added is firstly the second term, which is just a regularizer to just make the... Okay, I needed to explain this before. So the idea is that here we say we just express any points in the original space via the matrix, the original gram matrix that I described in the PCA. So it's just the snapshots of the data, but multiplied by some weights, you know. And these weights can just define these any points in the original space. And the only thing that I said about the second term is that now we, by using this regularizer, we just make it to be bounded. And fortunately, this kernel ridge regression problem has an optimal solution, which is just described here. So in our method, when we want to just come back to the original space, we need to solve this problem and then just bring back everything from reduced order space to original space. That's the step that we need to do extra, just in comparison to PCA, to come back to the original space. And in many applications in the reduced order modeling, this is not very important because they usually use this, for example, KPCA for the regression. So they just need to work in the reduced order states. They don't need to come back to the original space. But in our application, we needed this backward mapping. That's why we had to also work on it a little bit more. But of course, this is doable via this method that I just described.
And could I ask you to show, could we take a look at the code performing this kernelized ridge regression? Is it a part of sklearn?
Yes,
Well,
yes, I can show you. So, okay, actually, okay, but I can show you this thing. So this is a function inverse transform. But of course, maybe I can show you something now in the code and then immediately after that. So just consider, just imagine this case of KPCA. Yeah, just consider this part. So we are just using this class of KPCA, and then we just initiate with an instance of KPCA, and then we fit transform it, and we just input the matrix that we want to reduce, and then the output is XPCA, the reduced order state, and then we just use this inverse transform function to bring it back to the original space.
And this function inside the sklearn is using this regularizer.
Exactly. So it's not as a compact form as I showed you, but in this inverse transform function, we have this MP dot, and this dual coefficient is just computed somewhere above.
It's like the omega you showed in the paper, right?
Yeah, it's here. It's yeah, exactly. Yeah, it's
okay.
And the only difference is that here in the paper, I just showed this inverse here, but since finding this inverse is not easy in all the cases, so here in scikit-learn they just use a solver to just solve this problem instead of finding, because it's not possible to find the exact value. So here you can just accept some tolerance and just pick the value that you want. And here, for example, this is they're just adding this kernel with this alpha, and this alpha is the same regularizer that I mentioned.
Right. Okay. Nice.
Okay.
It's crazy to see. I mean, how many steps, how many assumptions are taking along the way, but even though you approximate things not exactly, because the reasoning is better, you get a better result. So I don't know. I get this feeling from this pipeline.
Yeah, that's true. So this was the first nonlinear method, and the second one that we described in this paper is a very known method in the machine learning domain, which is called autoencoders. So autoencoders, as you can see in this picture, are neural networks that are just looked like this. So we have two sections, as you can see here. The first part is called encoder, and the second part called decoder. So in the encoder part, we just reduce the. Okay, we are just training this network such that after just compressing it and decompressing it, we are just copying the same thing in the output as input. So we are training this model to have this input and output the same. And of course, since we are just working in this reduced order modeling domain, we need to have this Z vector, which is called the bottleneck of the network, having less neurons with respect to the input and output. So it's the same as what I said before, and the interesting point is that just comparison between this figure and the right figure. If we just assume that you have just one hidden layer in the middle, and you just use some linear functions to come up to this Z vector, it would be the same as PCA. So the algorithm would be the same, Of course, the method is completely different, but the result would be the same.
Right.
Okay, and okay, for the training of the network, we just use this L2 norm to find the best weights in this structure. And now let me go to the results. So to just be sure that everything is working fine, we are first using some toy cases that are known before. So we just selected this Lorenz system. Lorenz system is a chaotic system that I just put a GIF here that you can just have a look at.
Nice.
So this is just the behavior of this Lorenz system. So we have this chaotic behavior in the middle, so you can just jump to the different metastability. And this is a three-dimensional space, and this is the differential equations that we are dealing with for this system. And what we are doing in this toy case is that we use some Legendre polynomials to do what? To bring this three-dimensional system to a higher dimensional system, as I said here, to a R2 and to R128. So we are bringing this system from R3 to R20. So we are lifting this system by purpose. So we are just describing this system in a higher dimensional system, a higher dimensional space. And then we use the same procedure as I said for with using PCA, KPCA, and autoencoders. The good point here is that now we know that reduced order states, so now we can just easily verify that this pipeline works perfectly. And here I showed you how what linear mapping that we came up to just bring this three-dimensional space to 128. Okay, for the Lorenz system, okay, I think I have something here. Not this I will show you, and this is okay. So this is for the Lorenz system for the autoencoder. So this is the network that we came up at the end for the autoencoder, and here I can just show you. I mean, whenever I just come here, I can also come here, so there's no difference, but. So it's 166, so I can show you from here. So, okay, the thing that I didn't mention is that here we can just bring this three-dimensional to 128-dimensional linearly or non-linearly. And in this case, so here in the code, we have two cases of linear and non-linear, and for each of them, we have different kind of mapping. So I'm just looking at the non-linear part. So we have such a network. So we have the first part, which as I said, is called encoder. So we are just bringing the space from that 128 to a latent space that we describe here as 3, which is known. And here we are just bring it back from 3 to 128. So this is how exactly we can define this autoencoder class using TensorFlow.
So is that an autoencoder configuration that is common for the type of system you're trying to analyze?
Of course, the architecture is the same, but for example, the number of neurons, layers, and activation functions are different. But because this thing that I showed you here,
because these autoencoders are very sensitive to the number of layers, number of neurons, and all of that, right? So, and I can imagine, like it's a immense hyperparameter space to optimize, right? To find the right architecture for an autoencoder on a complex dynamic system you want to analyze, right?
That's true. That's very true, and that's why in the paper, not for the Lorenz system, but for the density, we also used some hyperparameter optimization to tune the network. But as you said, I mean, it's not that easy. Of course, this structure is not taken from any papers. I mean, this comes from one of our previous forks, but for the density, we just came up with the result as a conclusion of the hyperparameter optimization. So here, this is the result of the network for that encoder for the Lorenz system, and we performed the same the analysis of PCA and KPCA as I discussed before. And here we have the result for the L2 norm of the reconstruction. So we just compare the input and output for the different methods. And here you can see that this KPCA is better than these two. Of course, autoencoder is better than PCA because it's a nonlinear method. Yes, and I need to also mention that here I said we have this optimization for gamma. So in the kernel that I said above, we have this beta for kernel parameter. So we also optimize this beta to have the best result. Okay, now I can go to the real case, thermospheric density. So first I need to talk about the data. So we took the data from a database called high accuracy satellite drag model that I also put the website here. So, okay, it doesn't work. Why?
I think the hyperlink is...
okay,
could you open it?
Okay. I don't know why.
Is it working from here?
Yeah, it's working. So this is the website, and the data is public, but it's not easy to download. So you have to just create an account, which is free, and then through your account, you can just download the data here. And the data, okay, let me just cancel it. And the data has a resolution of 25 kilometers in the spatial and 10 degrees in latitude and 15 degrees in longitude, and has a temporal resolution of 3 hours. And for this paper, we took the data of 2013 in the altitude of 500 to 600, because the data is available from 300 to 800, if I'm not mistaken. But we just focused on this specific region. And then this is here that I said we just use this cross tuner to just optimize the architecture of the network. And these are the things that we played with. So we just assume that the number of layers can be from 1 to 3 for each decoder and encoder. And on each layer, we can have this amount of neurons. And the bottleneck of the network can be from 5 to 10. And of course, keep in mind that I put these numbers for different layers, but we are just keeping the structure of the autoencoder as I said. So we have we always have less neurons in the next layer. So we just keep this structure as I showed you here. And then out of this hyperparameter optimization, we came up with this network. So the input is 920, so it is the original space, and the latent space has a dimension of 10 with 3 hidden layers. And this is the result for the thermospheric density. So this is the same thing that I showed you for the Lorenz system, the L2 norm. And you can see again KPCA is better. But here, for example, you can see autoencoder is much worse than PCA. But here the problem is that for the Lorenz system, we could easily just generate more data because we had the differential equations. So we could just simulate it for how much we want. But for the density, we have just this specific data sets. So for sure, we are just suffering from the lack of data in this case. But anyway, for this specific data set, which is very famous in this domain of thermospheric modeling, we came up with this with this KPCA, which is much better than the autoencoder. And we also put this L infinity norm of the error to just show that, okay, this is a little bit higher than this, but the idea is that we both have the norm, a lower norm in KPCA and a lower spikes in the error norm in the reconstruction. Okay. Again, we just performed optimization for gamma in the kernel, but here we just went one step more. So we just showed this graph, which is a reconstruction error based on different values of gamma. And the point is that, okay, it doesn't go. And the point is that as we are just increasing this kernel parameter, if you remember, I said that this kernel parameter is just multiplied by the norm of the x minus y squared, which is the same as decreasing the variance. So let me just come back here. So this beta is the gamma that I showed you later. And in the sense of Gaussian, you can say that by increasing this gamma, you are decreasing the variance which is in the denominator. Meaning that by increasing this gamma, we are decreasing the variance. And by decreasing variance, we mean that we are just taking the information at a specifically point that we are just comparing, we are computing the pairwise distance. No, here, okay, I'm going back and forth many times. And so here, this x minus y squared. So when we are decreasing the variance, it means that we just take into account the points which are so close to the original point xi, and we are just neglecting the other points. And this means this. Okay, in the machine learning we have the definition of overfitting and underfitting, as I said here. And here, when we are just going in this direction, we are kind of overfitting because we just take the information of the point which is so close to the original point. So it means that maybe in the training data, we are just minimizing the error. But when we are doing it for the validation data, the error just gets higher and higher. And it's the same for this side of the spectrum. So by decreasing this gamma, we are increasing variance. And by increasing variance, it means that we are taking information from many points. And it means that the difference between close points are not visible anymore. So again, we are just losing some information. That's why we have such an optimal place for gamma to minimize the error for KPCA.
Right. I have more of a comment. I mean, and I hate saying this expression because in conferences. Okay, sorry. But I remember in fluid dynamics, there's something similar. I mean, we're talking about fluids again here. So in fluid dynamics, I remember basically when you introduce the continuum assumption, you say if the unit measure you're considering is too small, then the assumption breaks down because fluids are not, you have to consider individual particle interactions. So like the thing you were saying about the variance being too small. And but the same thing cannot happen when you consider big volumes of fluids, because then you cannot say that the temperature of a room is one number, because maybe, you know, in one point is something, in one other is something else. And so you have this, how's it called in English? The good in-between region that for which your assumption works. So it looks similar, at least.
Yeah, I mean, of course, what you're talking is, I mean, this kind of description is not common, at least in the work that I did. But the ideology is the same, you know. So, for example, right, if I want to just mention another point of view, so from mathematical point of view, then you are just increasing this gamma. As I said, I mentioned the Grimer matrix. So when you just increase this gamma and you are decreasing this variance, you are just taking the same points, right? So this means you are sparsifying the matrix, because you just because in the Grimer matrix, for example, in the first row, different columns are the evaluation of this kernel matrix with respect to different points in the system with respect to the initial point, right? And when you just decrease this variance, it means that the points which are close to the original space, the first point, have a higher value in the kernel function, has a higher evaluation in the kernel function, and the rest are close to zero. Just imagine a Gaussian distribution, right? And it happens again. I mean, likewise in this domain. So by just decreasing gamma and increasing variance, you are just populating this granular matrix. So what I was trying to say is that this is the same phenomenon, but from different contexts, we can just interpret it differently, you know?
Right. And for the records, I wanted to say Goldilocks region. That's the expression I was looking for. Just the in between.
Okay. Okay, and the next thing that we did is that, okay, for the autoencoder, we said, okay, we came up with this 10 number of states in the lower dimensional space. But for PCA and KPCA, it was, I mean, there was no optimization on it. So we just performed the 3 methods on different number of the modes. And by modes, I mean the latent space size. And you can see that the result, I mean, beside this initial part, is just compatible. So in PCA and KPCA, by adding different modes, you are just having more contribution on the variance. So you have more information from the original space. That's why your error just gets lower and lower. But for the autoencoder, it's not necessarily true. So in general, yes, but from point-wise, it's not true. It's not guaranteed that by adding a number of neurons in your bottleneck, you would just get a better result. And to just show and just make it more sense, we try to show you the data for a specific case. So at midnight of 1st of January 2013, at altitude of 500, you have such a density field. So this is longitude, latitude, and this is the value of the density. And here we just show the error. Okay, I think I did a mistake here. So this is the error for the PCA. Maybe I can just maximize this. This is for the KPCA, and this is for the autoencoder. So you can see that the maximum error here is higher than this. Okay. And then the last thing that we did is that, okay, we just said, okay, we analyzed the data for 2013, but we are not sure that if we have different data sets, we may just achieve different results. So to just resolve the issue of the stochasticity of the system, because at each time we can have different data, we analyzed the different methods based on different data sets from 2011 to 2019. And here again, you can see that the comparison between different methods are compatible. Of course, the trend of the reconstruction error based on different years are not monotonic, but this is not something that we can care, because this is just the data. So maybe we had some errors in those data, or maybe the data was smoother. I mean, we have no idea. But the important point about this figure is that the conclusion that we came up with the importance of KPCA is constant through each year.
And one question about that figure. So the model is trained on 2013, and then the same model is used for all the years, or you do hyper-optimization?
Actually, yeah, that's a good question. So you could do that, but what we did in this figure is that for each year, for different data sets, we just trained all 3 autoencoder, PCA, and KPCA for that specific year. And then for the next year, we again train the data for that specific year.
Okay, but also the hyper-optimization, I mean, also gamma and the layers.
So yeah, I was going to ask about that because I see you did parameter optimization for the kernel method. Have you done anything with your autoencoder? I mean, they're much lengthier to train and run, but have you looked at different configurations?
Sorry, I mean, of course, I said we did the hyperparameter optimization for autoencoder for 2013, but when we performed this analysis, we didn't optimize the architecture for the autoencoder and also the gamma parameter for KPCA. So we use the same.
So the gamma is fixed.
The gamma is fixed and the architecture also is fixed. Because the whole point of this figure is that if we just come up with this architecture, can we rely it to different kind of data or not? You know?
Okay, like next year data that are not out yet. You would like to have a model that can work next year. I mean, the idea is that you can do. Yeah, next year. I mean, reason.
Of course, in a real case, you have this kind of training all the time, so you are just always taking different data. But the idea is that it's something like a Monte Carlo analysis. So you just perform it multiple times to be sure that the results are reliable.
Mm-hmm.
And then we see that, okay, everybody is just moving in this direction of machine learning. But we wanted to see that, okay, I mean, for example, we are performing this analysis for the autoencoder, but is it worth it or not? You know, so we just calculated the execution time and the power consumption for different methods. And for this, we used this Pca library. That okay, I didn't put it here, but
I guess you could do.
Okay, I need to. Okay, let me just find the link. Okay, this is the link. Now I can show you here. So I can just add annotation here.
Okay, yeah, I was thinking because you can also add it from the components.
Yeah,
you can click edit and then plus.
Okay.
Nice.
Hopefully it works.
Yay. Okay, so this is the library that we used, Pca, to compute the execution time and the power consumption. For sure, in Python, we have easier ways to calculate the execution time, but for the power consumption, we use this specific library. And the only thing that we did is that here in the code, for example, here, we just call this function, and we put everything we wanted inside this function, this kpca script, and then we just call this script, this function, and then it just saves all the execution time and based on some numbers that is introduced in this library. Here you can just interpret it into the energy. And okay, maybe let me come back to the paper. So here you can see that autoencoder, of course, much higher because we are just training and training and training. And it's needed to be mentioned that for the autoencoder, we didn't include the time we spent for the hyperparameter optimization, but for the KPCA, we included the time for optimization of gamma. So if I exclude the optimization for gamma, of course, KPCA is comparable to KPCA. So it's around 1 second. And again, also for power consumption, you can see that is 40 times higher than KPCA. So we may try to just get better results with machine learning, and even in this case, even we cannot compete, but we are wasting so much energy on it. So that would be a good question: that is it worth it or not? And as a conclusion, I can say that we showed this Kernel Pca can be a promising method, but of course, in the introduction, we also said that in this domain of order reduction, the data set is so important. So, for example, the autoencoder can be better for some other data sets, but for this one, which is very famous, is not performing very good. And this is the part that is related to the previous paper. So in the whole pipeline, when we just compress this data, then we just put it inside a different algorithm to find the governing differential equation. And then the final model goes into an estimator to estimate the state of this satellites. So when we are just improving this step of compression, of course, everything just snowfalls, and we would have a better result in the final propagation. And for the future works, we use autoencoder, but convolutional autoencoders are also, mentioned in the recent papers. So this would be something that we can think of. And about the Kernel Pca is that okay, we use the Gaussian kernel, which is very famous, but we can come up with some kernels by our own. Of course, it's not that easy, because if you want to come up with your own function, you have to be sure that this is compatible with your model. So you have to be sure that the dynamic system is gonna behave according to the function that you are saying. For the Gaussian, it's not important, because it's a Gaussian distribution. So you always have all the contribution. But for different kernels, it's very important, because for this specific paper, I just tested all the kernels inside the scikit-learn library, and this was the best. And of course, the literature has always decided to use Gaussian kernels as well. And with that, I think I can conclude, but maybe I can just have a look at the code at last. So here we have, of course, this repository is public. So this is a GitHub repository that you can have a look. And if you have some issues, you can open an issue or making some pull request, so we can just improve it later. But for now, we have a function for SDC Lorenz. So this is the whole file that we just generate the different data sets for the Lorenz system, and then we train the network and compute the error. We have a POD, which is just used to compute the computational time and execution time, but in fact, we mainly use the Jupyter notebook. So in this notebook, we just at first, it's used for both Lorenz system and the density. So for example, in the first part, we are just loading the data, and then we do some pre-processing, take the validation sets and training sets. And then, for example, here, as I said, we are just computing the mean subtracted data. And for PCA, you have just this line. So you need to just transform into the lower dimensional, and then inverse transform the original space. For the KPC is the same. You just need to create this class, this instance of a class, and then you input the number of the modes you are interested in, then the type of kernel you want, and the value of the gamma and alpha. If you remember, alpha was the regularizer in the kernel function, and gamma is the kernel parameter. And okay, this is for the Lorenz system. So we just read the data that produced by this Lorenz file, and then we perform the same thing for the KPCA and PCA. And this is the error. And this is the part to find the best value for gamma. So it was, okay, I mean, there were different methods. So at first we tried to optimize both gamma and alpha. But at some point we ended up deciding to just optimize gamma because of a number of reasons, which if I want to mention one, is that, okay, the value of gamma that I mentioned, the value of alpha that I mentioned, I can come back to here. So the regularizer that I said, it's not part of the kernel PCA. So it's something inside this regression. And in practice, it's just used here, but this is completely, this directly comes here. And this is used to be sure that this inverse is always not singular. I mean, that this x transpose is not singular, no. So we are adding this thing. And so the point is that if you want to optimize it, it always gives you the lowest possible value for gamma, because if you just increase the gamma insanely, you are changing your matrix, no? So you are just finding the result of a different system. That's why in the optimizer, it always tries to just give you the lowest value. That's why at the end, we ended up deciding to just optimize gamma. And then that's it. So this is just a normal minimizer of SciPy. Also, we tried so this is a local minimizer and this is a global minimizer. And I think that's it.
Oh, this makes me want to dive back into machine learning like in the good old days. This is actually really fun, playing with all these different models and methods. There's some really interesting applications here for I think for notebooks and in general. Like you could make not the part, probably not the autoencoder. I think that's we couldn't like support doing a big cross validation loop where you do big changes to that. That would be too compute intensive for our system now. But all the rest we could definitely run in the executable notebooks. You could reproduce even the hyperparameter optimization that you run on the kernel method. So that we could also do. That'd be really cool. So we could make that figure, just produce itself.
Yeah, that would be very nice. But actually, the only thing that I was worrying is that we don't have the data in this repository because the data is bulk. So this was the thing that I was not sure if we want to load the data.
Yeah, we have to load it up. So there's two ways of doing that. One way is putting it in the repository itself, and other way, which is not yet implemented, but essentially you'll be able to upload a data component, and you'll have an IPFS. You'll have essentially a PID, persistent identifier, tied to that data that you can then use as an input to into your Jupyter notebook as a path, right? And it would essentially pull the data from IPFS, and it will be read directly by the notebook by VS Code.
Okay, that would be very nice.
And so when you add the component on the right, you can add data, and when you do that, you're actually loading those data on
so the tricky
Infora,
part,
Piñata, whatever.
Exactly. So we can load it from IPFS from your persistent identifier, which is tied to all the linked data structure in your research object. The part, though, that we have to optimize from a user perspective is that some users have their data into their repositories and others not. And that's particularly the case because, GitHub and other repo systems, they don't allow for arbitrary large data sets. And I mean, we don't allow that either, but we have a higher limit. So in some cases, so we have to think of a way so people can go into their repo and mark what is data and make a data component of that, like marking the files. Let's say you have a big CSV file in your repo. You mark that as data, and now you have an independent data component
Right.
that people can easily address, right? Because it's not intuitive. Let's say I want to download a data set from someone in my IDE. One way, it's not intuitive that I have to go in the code component and get the data, right? It would make more sense to go in a data component, from a user point of view. And because there's two paths to creating a data component, we're still kind of working on what's going to be the simplest for users, with the least burden to pull off.
I don't
I
know.
don't know if it makes sense to discuss about large file storage by Git. I think it's a parallel protocol that maybe could be integrated into a node, or I don't know, just thinking out loud.
We'll definitely have support for large files, right? Petabytes.
Mhm.
That'll be possible. Because we have a lot of people over at Protocol Labs that are really interested in helping with that. In the topic of scientific computing, especially, it's an important topic. So we'll have that support.
On IPFS.
But the thing is, on IPFS, absolutely.
Uh-huh.
And the thing is, though, it's really from a user perspective, right? How do you make their life simple? So, you're generating a lot of data. You want to share it with your colleagues. What's the best way to share it? What's the best way to get credit? And what's the best way to reach all your colleagues that matter? So those are questions that are fundamentally product development questions. And we're still thinking about that. We have some ideas. Hopefully, it'll come up in the coming next months or so. We'll have a functional data component.
Hey Vahid, I'm curious about your experience putting this together with the D-side nodes. What do you think? Pros and cons.
Of course, it was not that difficult. So it was, of course, working with that annotations was not easy. So, for example, just adding the hyperlink was not easy to understand. So, here it says that it's just it's based on somehow LaTeX, but the syntax was not similar to LaTeX. So
maybe that's probably because the first, it says Markdown LaTeX, and Markdown is another language, and
okay.
it's the
one. It's the LaTeX preview. Okay.
Yeah,
So
you have to add the $sign for LaTeX. So actually, you can switch from Markdown to LaTeX in that editor with the LaTeX syntax. But yeah, I agree.
So you can do href. Okay.
Yeah.
That might be a little tool tip we might want to think about adding. It's a very astute point.
Right.
What else? Though? What else did you enjoy it? Do you think it was very different from other ways of publishing your research or anything like that?
Of course, I don't know. This kind of open source stuff are not so common these days. Before. So of course, the thing that I am just adding everything here, so it's very nice. And I don't know. I was trying to do something, but I didn't at the end. But for example, we are working on a website called Research Rabbit. So you could just have a hierarchy of the papers that you work with, you read, to come up with this problem, with this paper. So here we can just add different papers here, I think. But for example, if we could have such a performance like Research Rabbit, to have a graphical view of the papers that are connected to each other, that would be very nice.
Right.
Yeah, that would be fun. I would just look at that too, just for fun. I'm sure it's very pretty to look at that web.
Yeah, it's cool.
Even just being able to, even without the graph, just being able to look at the paper and automatically from the references, the system creates hyperlinks that point to the open source papers that you're referencing. And so you can jump there in one click.
That's a tricky issue. If they're not associated with persistent identifiers. We could do it in theory. The problem is that we're not allowed to create, to automatize Google Scholar. So because Google Scholar has the best fuzzy search system, and it'll actually, we can give it like approximate titles with typos, and it'll find the right paper and then pull the PDF. Problem is we're not allowed to create robots that use Google Scholar. So that increases the complexity of automatically linking other papers by quite a margin. But who knows? Maybe in the future, Yeah.
Do you know, Vahid, the what they're using for Research Rabbit? Because they are, their system does that. You have the title and you can click.
Okay, I don't know if I remember my login. Okay, no, wait. What?
It's login.
Yeah. Even this was not very easy for me to understand how to work with.
Yeah, but here you can click on the PDF. In the Flying Through Uncertainty, there was the PDF available.
So how does this work, research habit?
Yeah.
Okay.
have no
I
idea.
see it. Yeah.
But you can click and you're there. It has to be open
Oh
source.
yeah. Yeah. That. Yeah.
But beside this research habit, this is a new initiative in, I don't know where exactly, but some of people in Max Planck are working on it. It's called MARDI, and it's also aiming the same open source research things for the researchers. And the good point here is that this, I don't know where exactly is the platform, the user interface platform, but the idea in this project is that it's not only just collects, I mean, for example, you just search a topic, and it not only just pop up the papers in that domain, but also the open source softwares and, I don't know, different databases in that domain. So it has every kind of the research article that you may need, which is not in the
Yeah,
research.
that's awesome. That's awesome. Having like we have really poor search capabilities for finding scientific artifacts like data and code. You know, that's a big problem. We're Google Scholar is great with PDFs, but everything else is a wholly different matter.
Yeah, but of course it's a nice direction that you're moving. I mean, I really like this open source stuff. Yeah, we want to be just in the have some fingerprints in this open source initiatives, because I mean we are just, I mean this paper is not submitted yet, but
Yeah, so what we're hoping to do, is that you can put all your research artifacts, your data, your code, maybe even a slide deck, a conference presentation, a talk you gave, and then we create a PID, persistent identifier, and you can add what we call a tattoo to your PDF document, and that's a link to your DSI node, and then you can take that paper and you can put it on archive, right? Where you want, with like in the usual communities that follow these types of works, and then they can find your paper, and then they're in their PDF viewer, and they can essentially click to see all the artifacts and connect to all your open source resources.
That would be very nice. Yeah.
Hey, thanks a lot for making this DSI node and testing the product in such an early phase. I really appreciate that. I thought the topic itself was interesting. It's again a topic that's dear to my heart because it touches machine learning, but it's also very new to me because I know nothing about these weather fields. So it was quite interesting to follow. So thanks a lot for that. I appreciate it.
Sure, no problem. Thanks for
Yeah, thank
giving
you very
me
much,
this.
Vahid. Let me say that I really enjoyed the presentation. You went smoothly from the I don't know how you moved from talking about atmosphere to ridge regression. I didn't notice. You made a good story, so it was nice to hear. Thanks for your presentation.
It was a good refresher on some linear algebra, I would say.
Yeah, also.
It's been a long time. It's been a long time.
Yeah.
So thanks a lot for that. Great. I'm gonna let
Sure,
you go
but
now. See you guys.
See you, Chris. Have a
Thanks.
nice day.
See you.
And thank you all for joining. See you next time, I guess.